Swayam Prabha. Digital India. Educated India.
We will continue to discuss about particle image velocimetry in this lecture. In the previous lecture, we got some introductory idea about the particle image velocimetry system. Let us see what is the role of PIV in modern aerodynamics. We discussed about capturing coherent structures or organized flow structures in aerodynamic applications through wind tunnel measurements when PIV systems are deployed. Therefore, you can apply it to different kinds of flow situations, of course to steady flow situations, but more interestingly to highly unsteady flow phenomena, where you can be having separated flows, time dependent flows on different configurations at high angles of attack, etc. Therefore, particle image velocimetry is a very important tool in studying a whole lot of complex flow phenomena which occur under unsteady situations. PIV enables spatially resolved measurements of the instantaneous flow velocity field within a very short time, and it allows the detection of large and small scale spatial structures. So, the structures again are not necessarily only large ones, but they comprise of a mix of large and small scale structures. For example, if you are looking at flow past an airfoil at moderate to large angles of attack, where the flow separation has initiated, then you do see that large eddies are formed around the body and they convect into the wake. Additionally, these large eddies break down into moderately sized eddies and still smaller eddies to extremely small structures. That means there are a range of scales, and this is an inherent characteristic of a turbulent flow field, where a repertoire of large, medium and small structures coexist. So, a PIV system has a challenge of spatially resolving all these structures. Additionally, if they can be resolved with very fine temporal accuracy, then that will be extremely ambitious goal fulfilled on both ends, spatial as well as temporal. Another need of modern aerodynamics is that increasing number of high quality numerical calculations require adequate experimental data for validation purposes. So, you do have a large number of high resolution numerical calculations, but we do not always have enough experimental data for validation, and validation is essential for numerical codes, especially the ones which have been newly developed, so that we can ascertain whether the physics of the problem has been appropriately modeled or not. Therefore, carefully designed experiments have to be performed, and the scientists who are doing the experiments have to collaborate and cooperate with scientists who are doing the numerical calculations, and there need to be a handshaking. The experimental data of the flow field must possess high resolution in time and space in order to be able to compare with high density numerical data fields. PIV techniques happens to be the most appropriate experimental tool for this task, because you are looking at spatial and temporal information. So, this is the best bet that one has for comparing with numerical data. And if information about instantaneous velocity field is required, then this technique can be used over a period of time, acquiring data, acquiring the time history with all the spatial structures resolved, so that finally when you lay the set of images in the form of a video sequence, then they can be appropriately compared with the numerical predictions. However, in order to perform PIV, there are a lot of requirements and challenges which the system should be fulfilling for you. The PIV system for investigation of air flows in wind tunnels must be serviceable at low speeds for very low velocities of the order of say 1 meters per second, which occur within boundary layers, because that's where the flow gets extremely slowed down. So, PIV should be able to resolve that on one end, as well as the much higher speeds which may be there in the free stream, especially for high speed applications, where the flow velocities can go to several hundreds of meters when you are talking about supersonic or even hypersonic flow fields, and that too laden with shocks. So, PIV also has a challenge of resolving discontinuities in the flow field, the sudden jumps of velocity across those structures. Additionally, flow field over solids which are moving or deforming also have to be investigated. That means there are moving boundary problems. PIV has to adapt itself for such applications. Also, in large industrial wind tunnels, there are some very specific problems. There has to be a large observation area, and there could be long distances between the observation areas and the light source and the recording camera, because of the large scales which are involved in industrial wind tunnels. And there the system has to be appropriately designed and applied, so that the solution is still reliable and the operational costs are not too high, and so on. So, application specific challenges do exist. High spatial resolution of the data field is necessary, which we have already emphasized, to resolve large scale as well as small scale structures simultaneously. So, this of course influences the choice of the recording equipment. That means the cameras that you use have to have very high resolution. Also, the laser system along with the camera together must be functioning at sufficiently high frequencies, so that the images can be acquired that faster. The second important condition is that high density of experimental data is required for meaningful comparison with results of numerical calculations. So, the tracer particle image density, that is the number of particle images per interrogation area, must be high. A powerful seeding generator with high concentration of tracer particles in the measuring volume of the flow, even at very high flow velocities, would be needed for this purpose. Otherwise, the particles will get thrown very far apart at high velocities, and then you will not have adequate particle density in the interrogation windows, and then you lack resolution. As the flow velocity is measured indirectly by means of the measurement of the velocity of tracer particles added to the flow, the tracer particles also need to follow the flow faithfully. In general, we know that the particles need to be small for doing that reliably. However, the small particles would also scatter very little light. Therefore, there are contradictions here, contradictory requirements here. So, this essentially results in a third important condition for the application of PIV, that is a powerful pulsed laser which would illuminate the flow field even if it is laden with very small sized particles. So, put together there are a lot of requirements and challenges which are specific to the problem, but the more challenging the flow problem, the more the requirements, the more stringent are the requirements, more the challenges. This is a slide which we have seen in one of the first few lectures in the course. So, we are just revisiting it again. It is a good time to revisit, because over the last few modules we are discussing about experimental studies, experimental techniques, we are discussing about wind tunnels in general. So, in that initial lecture we had talked about experimental studies being conducted in wind tunnels, and wind tunnels are used for aerodynamic measurements, where we measure pressure on model surfaces, forces and moments acting on models, we do wake surveys, we do flow visualization, etc., so that we attain valuable understanding of the flow problem. So, in the last few modules we have discussed about quite a few measurement techniques. Now the point has come where we are talking about laser based technique, the particle image velocimetry technique. So, in this wind tunnel we had discussed about how a smoke flow visualization, for example, would look like. That gave us very useful qualitative information, but then if you want to have quantitative information, then you have to have a measurement technique like particle image velocimetry, which again is not confined to single point measurement. You can have the measurement done for a particular region of the space, a region of interest to you. So, here an airfoil section has been inserted into the test section of this wind tunnel. It has been illuminated with a laser sheet, and then the particle image velocimetry system has been used in order to acquire a series of images, and then they have been processed with post-processed with suitable software in order to acquire the velocity vectors. So, you have this kind of quantitative information now emerging using the particle image velocimetry system. Of course, for doing these experiments we need suitable model positioning system, measurement, instrumentation, etc., which we have discussed in earlier lectures. A little bit more on that airfoil experiment. So, here you can see the airfoil once again, and you can see the laser light sheet falling from top, and since the airfoil section is opaque to the laser light sheet, there is a shadow region which is formed below. So, we are essentially interested in the flow field on the upper side of the airfoil, and therefore, as long as the upper side is illuminated with the laser sheet, we are going to obtain the images on the upper side, and post processing them we should be able to get the velocity vector field on the upper side. So, we have the laser illuminated airfoil upper surface, and a 532 nanometer filter is used with camera to cut off the ambient light when performing PIV. When you look at the clean test section, that means without the model inserted, then you will be able to do the velocity distribution in the clean test section. So, between a mean velocity of 7.9 to 8.1 meters per second, 50 levels have been introduced, so that you get the range of colors spanning between those two velocities. And for seeding the flow, we have water based fog being used for seeding the flow. They are being produced by a fog generator, which produces extremely fine seeding particles, which are essentially the tracers for an experiment like this. Obviously, from the speed range you can figure out it is being performed in a low speed wind tunnel. And when you change the angle of inclination of the airfoil, then of course you are going to get attached flow for low angles of attack, and then as you increase the angle of attack you will go to the separated flow regime. When you do a time averaging of the images that you acquired, then you would get time averaged streamlines and velocity vector plots. So, on the left what you see is the attached flow, on the right you get a separated flow. Obviously, this is at a low alpha, whereas this is at a moderately high alpha. And then when you are looking at instantaneous velocity vectors, they would look like this. what you have at the bottom. So, at different instants of time, the flow field would change, because the moment the flow separates, the separated region is a highly unsteady region, and then if you look at the streamlines and the vectors, the velocity vectors, especially in the separated region, you can figure out that the structures that you see over here from one frame to the other do have differences. That is because of the unsteady nature of the separated flow. So, we are able to get a glimpse of how the whole thing essentially works when we look at such images. Now, we will get into a little more detailing of each and every detailed aspect of a PIV system. So, we are going to look deeper into the tracer particles or the seeding particles, what kind of particles should be used for what media and so on. So, as we have already discussed, that PIV is based on direct determination of two fundamental dimensions of the velocity, length and time. That is why we have been talking about both temporal and spatial resolution. Now, the measurement technique is indirect because we do not measure the flow velocity directly, but we measure the movement of the particles, and thereby we obtain the information about the flow velocity, and it makes it imperative that the particles should be chosen suitably in order to avoid significant discrepancies between fluid and particle motion. We have talked about it earlier also, we are reiterating it here. We have talked about velocity lag earlier. Here we are introducing the Stokes law for spherical particles, which helps us to estimate the discrepancy between fluid and tracer particle movement in an accelerating flow. So, if the acceleration vector is given by vector A, then this expression essentially gives us the difference in the velocity between the flow field and the particle movement. So, the dP is the particle diameter, rho p is the particle density, rho fluid of course is the fluid in which the particle is laden, mu is of course the coefficient of viscosity. So, this law basically gives us some estimate about the difference in the velocities. Of course, if the densities of the particle and fluid match exactly, then there is going to be no difference at all. As the particle diameter increases, then obviously, because it varies with the square of the particle diameter, there could be significant differences in the velocity. Also, if the densities are significantly different, there would be significant velocity lags. Another important aspect is the relaxation time, which is a convenient estimate for assessing the promptness of particles to respond to local changes in flow velocity. So, typically smaller particles take shorter time to respond to fluid acceleration, and the relaxation time is given by an expression like this. Again, the relaxation time will be higher for higher diameter particles and higher density particles. For PIV in liquid flows, particles with matching densities are not very difficult to achieve. Solid or hollow particles both are used, and with appropriate fluid mechanical properties, if we can choose the suitable particles, then we should be able to minimize velocity lag as well as relaxation time. Typically, polystyrene in the range of 10 to 100 micron mean diameter, aluminum flakes between 2 to 7 micron mean diameter, or hollow coated glass spheres between 10 to 100 micrometers mean diameter can be used. However, high quality seeding in gas flows is much more difficult to organize, and usual choices again happen to be polystyrene, but now with much smaller size, 0.5 to 10 micron, different kinds of oils 0.5 to 10 microns. So, these are very small particles, the exception being helium filled soap bubbles, which could be much larger. A very important consideration here is health consideration, because There are experimentalists who are going to handle these wind tunnels, and if it has an open test section, then there could be a problem. If it is an open circuit wind tunnel, even there could be a problem. The experimentalists may be inhaling the seeded air, which could be a health hazard. Seeding distributors like rakes, fog generators, Laskin nozzle generators are widely used for dispersing these seeding particles. If the density of the tracer particles is identical to the fluid medium, we have the situation of neutral buoyancy, which is ideal. If the particle density is higher, the particles would tend to sink or settle down. That means the trajectories will be distorted in a way that the particles tend to follow the direction along which gravity is acting. On the contrary, if they are lighter, they would tend to rise because they become buoyant in the heavier density fluid. So, that is a little bit about tracer particles, specifics about how we choose them depending on the media. Now, there is also another very important aspect that we have talked about, that how to illuminate them. So, there is an issue of light scattering, which is very, very important in order to get them visible in the images effectively. There are two scatterings that we need to be aware about, the Mie scattering and the Rayleigh scattering. So, we saw a range of mean particle size diameters in the context of seeding or tracer particles in the previous slide itself, and we saw that between gases and liquids there could be significant differences. The particle diameter should not be too small, as light scattering properties have also to be taken into account. That means, even if they need to be small from the point of neutral buoyancy and other issues like velocity lag and such requirements also have to be fulfilled in harmony with the requirement of illuminating them. The particle image intensity decides the contrast between illuminated seeder particles and the dark background in PIV recordings. So, this contrast is directly proportional to the scattered light power. It is recommended that image intensity should be increased by properly choosing the scattering particles, then by increasing the laser power. So, increasing the laser power is not the preferred option. The choice of suitable particles and suitable sizes has to be done carefully, so that most of the light scattering issue is resolved there itself. In general, the light scattered by small particles is a function of the ratio of the refractive index of the particles to that of the surrounding medium, the particle size, the shape and their orientation. Additionally, the light scattering also depends on polarization and observation angle. So, there are many factors which could influence. Now, coming to the two scattering modes. Mie scattering, it is elastic scattering light of particles that have a diameter similar to or larger than the wavelength of the incident light. This is a very important fact which has to be kept in mind. The Mie signal is proportional to the square of the particle diameter. There is a strong angular dependency of the scattered intensity, especially for smaller particles, which has to be considered for successful Mie imaging experiments. Mie scattering is used to measure flow velocities in PIV. So, this mode of scattering is very important for us, and we get an idea about Mie scattering by looking at the Mie diagram for a case like this, where a 1 micron oil particle has been illuminated with ND-YAG laser with a light wavelength of 532 nanometer. It is a green light, and the intensity scales are visible through the Mie diagram here. The light approaches from the left, which is taken to be 0 degree, the opposite end it's 180 degree, and the scattering is basically given by this profile. You can see that between circles which are indicative of the intensity scales, there is a factor of 100. So, in the angular sense, how the light scatters over a range of 0 to 180 degree, or typically between 0 to 360 degree, is visible over here. Rayleigh scattering is the elastic scattering of light by particles much smaller than the wavelength of light. And that is the case for gas phase molecules, and therefore this method is suited for laser imaging in gases. As we said, Mie scattering can be characterized by the normalized diameter q, which is dependent on dp. Scattered light intensity increases with increasing particle diameter. It roughly scales with q square. Scattering efficiency of particles strongly depends on the ratio of refractive index of the particles to that of the fluid. Now, since the refractive index of water is considered larger than that of air, the scattering of particles in air is at least 1 order of magnitude more powerful compared to particles of the same size in water. Hence, much larger particles can be used, or rather have to be used, for water flow experiments. This is certainly not a difficulty, because we have seen that density matching of particles in water is much easier to do, much easier to handle than in air. Now, from Mie scattering diagrams, it is observed that light is spread in all directions for small Cedar particles, and therefore there could be a lot of multi scattering in such situations. Here we have provided a Mie diagram again for a 1 micron glass globule in water with the same Nd:ER laser. So, we learned a little bit about illumination of particles. Next, let us briefly look at the light source, the laser. So, lasers are of course widely used in PIV, and it is because they emit monochromatic light with high energy density. Now, monochromatic light, which is light with a specific single wavelength, is easily bundled into thin light sheets, and these light sheets are important for us for illumination of the seeding particles in the test section of wind tunnels. Now, lasers comprise of 3 main components: the laser material, which consists of an atomic or molecular gas, semiconductor or solid material, the pump source, which excites the laser material by introduction of electromagnetic or chemical energy, and a mirror arrangement or the resonator, which allows an oscillation within the laser material. Now, from quantum mechanics, we know that a particular atom can be brought to various energy states by means of 3 elementary kinds of interaction using electromagnetic radiation. One of them happens to be the recipe for lasers. Now, these interactions are absorption, spontaneous emission, and stimulated emission. In absorption, what happens is that from a ground level E1, the atom rises to the excited level E2 when an incident photon emerges and is incident on it, raising it to the excited state. In spontaneous emission, the atom from an excited state drops to the ground state, emitting a photon which is randomly directed. And of course, here the difference between the energy levels is given by a product of h nu, where h is Planck's constant and nu is the frequency. So, we already talked about absorption and spontaneous emission. When it comes to stimulated emission, this is the diagrammatic representation. Let us try to read the lines as we look at the diagram as well. So, an incident photon stimulates an atom in the higher energy excited state E2 into a specific non-spontaneous transition to lower energy state E1, and then in addition to the incident photon, a second photon is emitted in phase with the former photon. So, there is a second photon which gets emitted. Therefore, the impinging wave gets coherently amplified. So, this is basically the principle behind amplification of the incident wave, which is achieved through a laser. So, for large number of atoms, one of the two processes, namely absorption or stimulated emission, is predominant. In case of population density inversion, that means where you have a number of excited atoms greater than the number of ground state atoms, and which of course can occur only under thermodynamic normal non-equilibrium conditions. So, you have a situation where N2 exceeds N1, you have stimulated emission which is predominating, whereas when N1 is greater than N2, that means the number of ground state atoms are larger than those of the excited state atoms, absorption dominates. So, this is the basics of laser, and in PIV, in low speed PIV applications, we have neodymium YAG lasers, or briefly called ND YAG lasers. They have two wavelengths at which they can emit, and they are the most important solid state lasers. The laser beam is generated by Nd3+ ions, and Nd3+ ions can be incorporated into various host materials. For laser applications, YAG crystals comprising of yttrium, aluminum, garnet are commonly used. They have very high amplification and good mechanical and thermal properties. Excitation is achieved by optical pumping in broad energy bands and non-radiative transitions into the upper laser level. So, this is a brief about ND YAG lasers, which are widely used especially in low speed PIV applications. When it comes to high speed PIV applications, the choice would be neodymium YLF lasers with lambda of 1053 and 526 nanometers. They of course require reliable high average power laser source when it comes to high speed PIV applications. YLF stands for yttrium lithium fluoride. These lasers produce high pulse energy and average power in their category, with repetition rates which can go up to several kilohertz. Therefore, the rates are way higher than what you can normally see from ND YAG lasers. They can be operated at different fundamental wavelengths. The fundamental wavelength most frequently used is 1053 nanometer, but which is turned into a visible range at 526 nanometers by frequency doublers. The same principle is used even in ND YAG lasers, where you can have 1064 and 532 nanometers. So, this was a brief about lasers that are used for PIV applications. So, in this lecture, we discussed about the role of PIV in modern aerodynamics and the accompanying requirements and challenges which it should fulfill. We had a brief look at PIV images for attached and separated flow past and airfoil tested in a low speed wind tunnel. Subsequently, detailed discussion on different components of the PIV system was initiated. We looked in more detail regarding the tracer particles, regarding the scattering, the light scattering from the tracer particles, and the light source, the lasers. Thank you.